Hello guys, welcome back to the channel. In this video, I'm going to show you how to transform a discrete point dataset with its own unique values like this into a seamless interpolated raster like this using spatial interpolation techniques and a couple more other alternative examples which can also be quite useful when trying to learn this concept of producing maps based on spatially scattered point datasets. Now, this sort of interpolation methods can actually be utilized for a number of use cases. Well, off the top of my head, if you have a set of points which define elevation of a certain area like this, and if you would like to create a surface using those points by generating values for these unknown areas using a mathematical formula, which we also end up calling the method of interpolation, we can quite simply use this approach to do that sort of things using QGIS. And the example that I have chosen today is a case which illustrates a pretty similar application of this concept, but I'm going to make use of average yearly rainfall records at a specific location, and I'm going to present you with a few ways of how we can transform this information into a map which shows spatial variations of these average annual rainfall records. So before we dive into the details of this method, let's have a quick look at the dataset that we have in hand today. So as you can see over here, I have loaded up a point shapefile into my layers panel called average rainfall, and the rainfall values are in millimeters. And right over here in my QGIS workspace, you can see how the points are scattered across the area. Now you might be curious to know what each of these points represents, and as I told you guys, I'm using an average annual rainfall dataset for the purpose of this tutorial. So what I'm going to do is I'm going to open up the attributes table simply by right clicking over here. And I'll go to open attributes table, and this would be my attributes table. So over here you can see that we have three attributes or three fields. We have the ID column, station ID, and the average rainfall value in millimeters. So each of these points actually correspond to a specific station. You can see over here the stations are numbered from number 1 all the way until number 27. And for each station we have an average rainfall record, well, which varies from 820 all the way until 2600 millimeters per year. And what we're going to do today is we're going to try out a few methods that will help us visualize the distribution across this selected area using a couple of interpolation methods. And to do that, I'm going to get started with one of the simplest methods out there to generate such a map which shows the distribution of rainfall across this region, and that's using Voronoi polygons, which is going to be one out of the three methods that I'm going to discuss today in this tutorial. Now, Voronoi polygons are actually a very commonly used method for partitioning a space into regions based on proximity to a set of points. And each point in the input dataset is going to be associated with a unique polygon in the output that we're going to generate. So if that all sounds a bit too complex for you to grasp, let's dive right into the tool and see what sort of an output we are going to generate. So I'm just going to exit out from this attributes table, and what I'm going to do is I'm going to go to processing and open up the processing toolbox, and from here I'm going to search Voronoi polygon. So that's under vector geometry, and you can see the tool right over here which is called Voronoi polygons. So let's double click over here in order to open this up, and you can see that we don't really have to specify that many inputs for this tool to run. We just have to give the input layer, and by default you can see that it has already selected the layer that I have on my layers panel, which is this average rainfall value in millimeters. And what I'm going to do is I'm going to save this into a permanent shapefile rather than having it create a temporary layer. So let's browse to the place or the location that I would like to save my shapefile in, and I'm going to call this the first method that we're going to explore today, and that's Voronoi polygons. Click save, and as you can see over here, our output is actually going to be a shapefile which gets added by default right over here to the end of the name that I specified, .shp. And after that we can just simply go ahead and click run, and you can see that immediately it generated a bunch of different polygons. Now you can verify the data type by heading over to the properties, and if you head over to information, you can see that this is of the type S3 shapefile, and the geometry type of it is polygon. And over here we can see the coordinate reference system. It's in WGS 1984 Geographic Coordinate Reference System, which is the same coordinate reference system that I'm using for my project, which you can see right over here as well. And if you open up the attributes table of this Voronoi polygons shapefile, which was the newly generated shapefile, You can see right over here, we have the same set of fields and the same records that have been transferred over from this point dataset into this newly created polygon shapefile. So if I just move this point shapefile over to this, you can see that each point has sort of been represented by one single polygon, because these polygons are generated in such a way that every point within a given Voronoi polygon is going to be closer to the associated input point than to any other input point. And since we have a dedicated column or a dedicated field right over here, which has its records pertaining to these average rainfall values, what we can do is we can actually go ahead and change the appearance of this shapefile by right-clicking over here, and we can go to Properties, and if we head over to Symbology, and instead of using one uniform color to represent each and every polygon like this, what I'm going to do is I'm just going to select Categorize over here. As you can recall, we had 3 fields, and the category by which I would like to assign the colors is going to be this average rainfall value. And when it comes to the symbol, well, let's leave this alone for the time being. And when it comes to assigning a color ramp, well, since we're talking about rainfall, I think it would be quite appropriate if we go with a color ramp like this, where we could show the areas with high average annual rainfall in dark blue colors and areas with low average annual rainfall in maybe light blue colors, or well, it goes all the way to white in this color ramp, as you can see. And just hit classify right over here, and as you can see, it has assigned a unique value to each of these different rainfall values that we had, which correspond to each of these different polygon. So when I click apply, well, if I just get this out of our way for the time being, now you can see how the rainfall distribution appears to be. Well, if you're really thinking about what sort of values we are dealing with, you can get an idea about that simply by expanding this right over here. So you can see that what each of these colors actually correspond to in terms of a rainfall value. Or what you could do is you could also head over to Properties and go to Labels and select Single Labels. And right over here in the place where you need to select the value, we're going to select the average rainfall millimeters, this column, which basically will display the rainfall value which corresponds to each of these different polygon. And we can maybe decrease the font size just a little bit. Well, I'm not really sure how this is going to appear, so yeah, I think this sort of font size should be good enough. And at the same time, I could maybe, well, get rid of this point dataset as well. And if you would like to sort of ensure, well, not the continuity, but if you would like to maybe get rid of these lines which clearly shows the break as we go from one polygon to another, what we can do is head over to Properties again, and under Symbology right over here in Symbol, just go to Configure Symbol, and under Stroke Style, make sure that you select No Pen and click OK and Apply and click OK. And now you can see that we basically got rid of those sharp black color boundaries. With this, you can see how the rainfall distribution actually happens across the region. So we can clearly see that the lighter blue colors right over here around the northwestern region indicates that this area is actually getting relatively lower rainfall compared to especially this area, which is the southeastern area, which seems to be getting quite high rainfall relative to the other numbers that you can see over here. And that's why it has been colored by this dark blue color. So even though I wouldn't really call this a seamless continuous map, because you can clearly see the sharp boundaries of each polygon, you still can grasp some sort of an idea about the distribution of rainfall within this region based on the spread of these colors. And this method, as I told you guys, is actually being used in the industry quite widely. However, if you're trying to generate something a bit more seamless, or something that has a bit more continuity when it comes to how the rainfall changes from place to place, then we can actually go with the second option, which is called IDW Geostatistical Interpolation method, which stands for Inverse Distance Weighting. And the IDW method is also particularly suitable for situations where you have a set of sample points with known values, just like what we have right over here. And if you want to predict the values at other unknown locations based on their proximity to these samples, which is not exactly what we are doing right over here. Because when using Voronoi polygons, the only thing that we are doing is we're just basically assigning an area of influence for each of these points, which we define as its own unique polygon. And we are just basically switching from polygon to polygon, which is defining its own area of influence based on the proximity of these points to each other. Alright, so what I'm going to do is I'm going to turn off this layer for the time being. And now I'm going to search for the next tool that I'm going to work with, which is called IDW. And right over here, you can see the tool, which is IDW Interpolation. And when it comes to specifying the parameters for running this IDW Interpolation tool, right over here, you can see that we have to select the point dataset again, which happens to be this average rainfall millimeters. And now you can see that it needs this interpolation attribute as well, which is not something that we necessarily had to specify when we generated these Voronoi polygons. But because in IDW method, what we're trying to do is we're trying to generate values for unknown points or unknown areas based on the rainfall value of the sample points. We would definitely need to provide this as an input, and we would need to direct it to the correct field, which happens to be average rainfall millimeters. And after that, I'm just going to click this plus button over here. And right over here, you can see that the vector layer that we are dealing with is average rainfall millimeters, which corresponds to this. And the attribute of that is going to be the average rainfall millimeters. And it's of the type points. And right over here, we are also required to specify the extent of the raster that we would like to generate. So there are actually a number of different ways of specifying the extent. And what I would like to do is I would like to maybe generate my raster covering all of my points, but not necessarily as a tight fit, but maybe extending a couple of meters beyond the furthest points when it comes to the 4 edges. And the easiest way to do that would be to actually specify it manually on the map by drawing a rectangle. So I'm going to go with this option for that. And all I have to do is just make sure that I specify which encompasses all of my sample points, and it'll automatically take into account the coordinates right over here, as you can see, in decimal degrees. And at the same time, we would also need to specify the output raster size. So I'm going to specify the pixel size of X to be 0.001 decimal degrees, and well, basically the same amount gets translated over here into the pixel size of Y as well. And with that, you would be able to see the number of rows in terms of pixels in the output raster. And I feel like this would be a fairly acceptable number of pixels that I can actually deal with depending on the specifications of the computer that you're using. And finally, I would like to save this into a permanent file simply by heading over to here and going to save to file. And I'm going to name this as rainfall_IDW and click save. And as you can see over here, it's not going to get saved as a shapefile anymore. The file that's going to get generated, it's going to be a raster, which is of a .tiff file format. And after that, click run. And this is just going to take a couple of seconds. And now you can see how the seamless raster got generated based on these set of points. Well, again, in order to give this variation of color a bit of meaning, what we can do is we can actually head over to this newly generated raster and go to properties, and under symbology, select single band pseudo color. And what I'm trying to do is I'm trying to do something quite similar to what I did with the previous dataset. And that's to specify a color ramp like this, which can show me clearly the areas with lower rainfall and the areas with the relatively high rainfall records. Well, you're not restricted by this blues color ramp alone. As you can see, you can actually go with a number of different color ramps and test out for yourself and go with the one that you see or that you think matches quite well with what you're trying to represent. But for this example, I think I'm just going to go with the blues again. Right over here, when it comes to the precision of the labels, I think I would just get rid of everything. I would like to just have this as an integer. And when it comes to mode, well, that's again a choice that you would have to make. If I were to go with this continuous mode, you can see how that appears. And maybe if I go with something like quantile, I would be able to increase the number of classes as well. Let's split this to 10 classes. So as you can see over here, it gets splitted into 10 different classes. And click OK. And click apply and OK. And I think this looks actually far much better than the previous representation. So again, from here you can clearly see how the rainfall actually varies. And again, as I told you guys, it's a clear indication that this region is having relatively less rainfall compared to this region. That's why this region is indicated with this dark blue color. But unlike the Voronoi polygons that we had previously, if you can recall, well, you see some sort of a similarity, isn't it? Because you definitely should see a similar pattern when it comes to these two maps showing us the rainfall distribution in a holistic way. You can see that when we use this IDW method, it basically uses its computation algorithm to fill in for these unknown areas as well. So if you head over to this identify features tool, and if you click somewhere over here on this rainfall IDW raster where we didn't really have any data points, what you would be able to see is the pixel value. So you can see that as I'm clicking on random areas where we didn't have any data points, you can see that it has generated a value by itself based on its algorithm. So that's the beauty of actually using this IDW method, because based on how the points are scattered, it'll actually try to interpolate and generate this kind of a seamless raster, which you can then use for a number of different purposes, such as interpreting how specific variable varies geographically across the region. So I hope you guys got the basic idea or the gist of using these interpolation methods to create this kind of seamless rasters. And finally, before we end this tutorial, I'm also going to show you another interpolation method that we can use, which is also quite frequently used in the world of geospatial analysis, and that's the Spline method of interpolation. And to access the Spline interpolation tool, similar to what we did before, we can head over to processing and open up processing toolbox. And right over here, if I search for Spline, you can see that the tool that I'm after is called Thin Plate Spline, which is under Saga Tools. So let's double click over here. And as you can see, the first input that we need to specify is the set of points, which is this one right over here, average rainfall in millimeters, and the corresponding attribute of that, which defines the spatially varying rainfall values, is going to be this average rainfall millimeters column. And similar to what we did before, we would have to specify an output extent as well. So I'm just going to do that by drawing on the canvas. Well, I could zoom it out just a little bit and maybe draw on the canvas like this. And it automatically grabs the coordinates of the extents, as you can see over here. And when it comes to cell size, well, you can see that the default value is 100, which doesn't really make sense when it comes to especially dealing with a coordinate reference system like EPSG 4326, which is using decimal degrees as its unit. So I'm going to change this to 0.001. Well, we'll just give this a go and see how it looks. All the other parameters corresponding to this specific interpolation method, I'm just going to leave them in the default values. And I'm not going to save the output of this into a permanent file just yet, because I would like to see how it looks compared to these other outputs that I have right over here before going ahead and saving it into a permanent file. So let's give this a go and see how it looks. And as you can see, we have a target grid which got generated just now. So let's see how that looks. And I think it would be quite easy to put all the colors back into the same scale that we are dealing with in terms of color by heading over to symbology, and we'll change this to be quantile as well and set the same number of classes and click apply and click OK. So now you can see that even though again it captures that holistic variation of rainfall across this region by giving us the indication that this area has relatively less rainfall and this area has relatively high rainfall. If I were to compare these two, the output that I generated using Spline method and the output that I generated using IDW method, you can see that it's not quite the same. However, both of these retain that holistic qualities when it comes to how that variable changes over different areas. So the point that I'm really trying to project across to you guys is that there's no right or wrong interpolation method. It all really depends on what you're looking for. For specific applications, some interpolation methods might be quite suitable than others. The best thing to do is to actually try out a number of different interpolation methods and see how the results look and go for the one that you think is the best. So based on the results that I have over here, I'm more inclined to actually go with this IDW method, particularly considering its smoothness when it comes to how it generated this seamless raster going across all my known data points. And finally, before we wrap up this tutorial, I would also like to show you guys that we can generate a set of contours based on these generated rasters. And when we have a set of contours, it's also going to be quite easy for us to sort of read the numbers in between. So to generate a contour map, I'm going to this processing toolbox again, and I'm just going to search contour, and under GDAL you can see that there's one tool called contour, and as the input layer I'm going to generate my contours based on this IDW raster. So I'm going to select this, and the interval between contours, well, by looking at the variation of the numbers, you can see that we have the lowest number to be about 833 and the highest to be about, well, 2600. So based on that, I'm going to select the interval to be about 100 meters. And after that, I'm just going to go ahead and click run. And you can see that based on that, it actually generates a nice set of contours, which you can then go ahead and change the color to make it a bit more apparent. And if you check the attributes table, you're definitely going to see this rainfall value under this well, elevation column. So what I could do is I could actually add those numbers as labels to these contour lines by selecting the appropriate column over here. And let's decrease the size a bit, and we'll see how it looks. Yeah, now you can see that it really has that professional touch in it when it comes to showing us how the rainfall actually varies across this region in terms of the variations of colors as well as the actual numbers. And with that, guys, I think we've come to the end of this tutorial, and I think you guys got a very clear idea about using interpolation methods to generate this kind of seamless rasters using a point dataset, just like what we had at the beginning of the tutorial, and also how these kind of seamless rasters actually differ from this sort of a Voronoi polygon representation. And guys, if you do have any questions, you know what to do. Add a comment down below and I'll get back to you guys as soon as possible. And if you did like the tutorial, you can show your support by hitting that like button. And at the same time, if you'd like to stay tuned for this kind of interesting GIS related tutorials, don't forget to hit that subscribe button as well, because we are publishing videos quite frequently, and trust me, you don't really want to miss any of them. Thanks a lot for watching, guys. I'll see you guys again with another tutorial soon.